On behalf of the IEEE Communication Society, it is my distinct pleasure to welcome you to the 2025 Montreal Salon for Future Communications in the historic and beautiful city of Montreal, Canada. The Montreal Salon for Future Communications provides us a unique platform to network with the leading researchers and colleagues in the global technical community. There are 6 panels for the Montreal Salon. We are so fortunately to have 12 well-recognized panelists from both academia and the industry to share the innovative ideas and the thoughts on AI and the 6G networks. They are Zhang Cioffi, Reinaldo, Valenzuela, Khaled, Letaief, Rahim, Tafazolli, Gerhard, Fettweis, Chengshan, Xiao, Alberto, Leon-Garcia, Tong, Kostas, Plataniotis, Zhang, and Peiying. We hope that you enjoy the program and the activities. I would like to acknowledge the generous support of the patron, which is indispensable to the success of this salon. The patron recognizes that the IEEE ComSoc community is the leader in advancing communications and networking technology and in empowering individuals in the community. IEEE Communication Society has been creating and promoting leading-edge communications and networking technologies for humanity through its premier conferences, high-quality publications, technology standards, and educational activities in order to best serve our 36,000 plus members worldwide in both academia and the industry. Finally, I would like to extend my sincere thanks to everyone here today. I wish all of you a wonderful time in Montreal. Thank you.
Good morning, everyone. I'm Chengshan Xiao, currently ComSoc VP Conferences. Before the panel, I'd like to mention we have Kostas as SP Society President join us, and Robert Sherman is our Communication Society President. He is not available today. And also Sabrina is the president from AES Society. So I just want to mention, because this is related to this panel. So let's get started for the talking points. First one is what nerve waveforms, signal processing, and the resource allocation schemes are essential for the emerging communication sensing and the efficient AI in the 6G IAM. Who would like to talk first?
Okay. Well, Reinaldo, Valenzuela. I think it's an exceedingly important question and exceedingly important topic, as per the chairman of the panel, with the opportunity to really do the transition into a brand new area of growth, which is sorely needed, I should say, or increasingly expected to provide new revenue stream from cellular providers and vendors in general. Now, in specific, in terms of waveforms, I would like to take a step back a little bit. And I think we are a little behind and maybe need to catch up with our radar colleagues, but at the same time, not quite exactly copy-paste. When you are trying to detect a target which could be against the open sky, it's a very different problem when you're trying to detect a person amongst a crowd. And so I would like to suggest that before we can discuss waveforms, we should touch base with what ComSoc we've done exceedingly well over the last 50 years, which is what are the fundamentals? What is the Shannon of integrated communication and sensing? And of course, it has to be deployment scenario specific, but to be a truly integrated, we're talking about reuse of existing infrastructure. So think of rooftop antennas. Maybe the easiest one is a monostatic, so transmit, receive in rooftop. Ideal scenario for service provider to get dual use. But now you're trying to detect a car, a person, in the midst of what radar people would call ground clutter. That's horrible. This is the worst possible scenario. And on top of it, maybe a number of interesting cases are non-line of sight around the corner. How many points in the street you actually see from a rooftop antenna? Or in reverse, when you walk down in the midst of Toronto downtown or New York downtown, how many times you look up and see antennas? Quite often, but not everywhere. And so before we can even talk about waveforms, what are the fundamental limits and the realistic conditions? What is the background? You know, always facial information, all of this estimation theory is going to be critically dependent on signal-to-noise ratio. Here, noise is mostly your background return power. Well, where is that data on this kind of scenarios, not in against the sky, against the ground clutter that is the classical? So, you know, a little controversial, but without answering your question on specific waveforms, I would say we need to do our homework before we can calculate those.
Thank you, thank you. I'm always scared to be sitting next to him because it's very, very controversial. And you don't want to go against him, that's for sure.
I take that as a compliment.
Of course I'm taking it as a compliment.
That's good. That's good.
But anyway, I think there is no question that integrating sensing and communication is one of the critical items for 6G. So in this context, I think we need innovative waveform designs. And I think this is a very interesting question that will try to optimize spectral efficiency, hardware performance, as well as, I think something that is going to be very important in 6G is this idea of task-oriented communications and semantics. I think they're going to be very important, and therefore these waveforms must, in a way, optimize what I refer to as semantic intelligence. So in this context, I think these waveforms, or I can think of, they need to be perhaps looked at in three different aspects. The first one, we need to be able to have what I refer to as sensor pilots for kind of environmental sensing, for example, target detection, and so on and so forth. And I still believe that task-oriented communication and semantic communication is important. So we need some type of what I refer to as semantic encoding, and this is for task-specific information transmission. And finally, I think Reinaldo talked about fundamentals. Fundamentals is still going to be there. Error correction is going to be important. So because I think when we start talking about integrated sensing and so on, line of sight is going to be important, and therefore error correction is going to be very important to improve the robustness against the channel kind of distortion. I think these are the three things, and I think it's important to emphasize when we start talking about 6G that we're talking about perhaps sub-6 gigahertz, we're talking about millimeter waves, and potentially terahertz. So this is also, we need to actually be able to, the way I see it, it's like enable these simultaneous wideband kind of sensing and communication.
Thanks, Khaled. So actually, we like to have if there's a controversial, it's even better for dialogue and for discussion purpose. We encourage that part. Even though we are colleagues, we share friendship, at the same time we share different opinions, will be even better. Thanks.
I just want to follow up with Reinaldo. I think in this case of integration of sensing and communication, the single point detection accuracy or to some limits is not important. The important thing is the networking between base station, let's say 10 million base stations around the world, and 3 billions of devices. That will put the sensing and the communication in a different setup. So this, first of all, this data will be the data that we never see before. So it's probably the human language 6 magnitude order of that amount of data. So with that data, Reinaldo also mentioned the clutter. I don't think that the statistic model is useful anyway, but we need a more precise the ambient environment model, because that's where the AI will heavily latch on that to deliver service.
Thanks, Wen. Any response?
I think we are in agreement, but a very interesting point about the networking. I'm a very pragmatic, walk before you run, so I brought up the monostatic. But of course, the potential of network sensing, as very ambitious if you consider all of the base stations network at the same time and all of the UEs, the amount of information you have potentially is overwhelming, is really vast. Now, that could have amazing capabilities, potential. At the same time, the demands on the infrastructure are going to be neck-breaking, but with huge potential. So that's a very interesting point of network intelligence.
Thanks.
Yeah, I don't disagree with anything that's been said, but trying to get to the fundamental point that was mentioned is, at least from my own perspective in looking at this and trying to resolve it, what sensing really brings is this concept of position. So in addition to this channel changing with time, you now have X, Y, and Z. And so the good ways, especially since we're more wideband, which means relative to physical motion, we have more data that we can use, is this predicting of the channel that's position and time, doing that accurately. As far as from a fundamental standpoint, you mentioned capacity and the multi-user capacity regions and so forth. I think those are known. We've made progress in that area. They are sensitive to the channel being known for it. What you do see is when the systems become congested, so in other words, there are more users active than there are degrees of freedom in the environment. So, and MIMO only goes so far. The rank of your channel eventually is limiting, no matter how many antennas. When that number of users that are active exceeds the rank of a channel, what we do today in the signal processing is no longer optimal. It is pretty close prior to that point, and there are factors of 10 power savings, so forth, or doubling data rates or range that are conceivable, but you have to get in to exactly how the signals are modulated, demodulated, and processed. I'm not saying change the OFDM or the codes that are used, but how those signals are processed. There's some nonlinear processing that becomes necessary in order to get to the best areas. So fundamentally, there's that position part to know it accurately, and then also recognizing there's some additional processing that we can do when we get congested to improve. So those two areas I see as opportunities, really, where not all the answers have really been developed to the point where someone could use them, and the computation that everyone's mentioned to support all of that will be important as well.
Thanks, John.
Okay, so for this question, I would like to add a different perspective, that when we see the question, so it's assumed that the integrated sensing and communication could be or should be done at the base station side. But if we consider the performance targets, the metrics, for example, the communication range or the detection range, they may not be the same, the scale. In that case, can we just consider the network deployment of, for example, communication base station or the sensing node in a different or superimposed the layer? For example, we may deploy more sensing nodes along with the, for example, the UAV flying route or pathway, and then put some of the traditional base station. Sometimes we could deploy the integrated sensing communication base station, or we separate two different sensing node, communication node in different the scale. Also, when we put into the 6G RAN in the context, also we have to consider some of the challenges. For example, the high frequency, high mobility, and also the high altitude. So they pose different research challenges, and especially when we consider the UAV communication. I know in some city, for example, Shenzhen, they have deployed the eVTOL for the initial commercial application. And then they have to guarantee that the flying route, then there's no the unknown flying vehicle or the UAV. So they have to guarantee the high accuracy of the detection to protect that the deployment of UAV or the commercial application. Then in that scenario, so the sensing and communication may be integrated all different ways. So that is also come to the network layer deployment. If we go to the physical layer, there are lots of discussions. For example, how we can address the high mobility, the fading channel, like the delayed Doppler channels, and there are some the signal processing methods put forward in the last, I think, the 5 to 10 years, and then how. But put into the context of high frequency band, like the millimeter wave or the terahertz frequency band, then that is the problem may be more different. And also, if we also consider the 3D, the communication channel, including high altitude, then the channel may be more challenging. Then the AI may help us communicate the users efficiently by learning this radio frequency environment. I see probably in the other slide of question, we will come to the detail of the AI. Yeah.
So the second point is what novel services and applications are uniquely enabled by integrated communication, sensing, and the AI 6G RAM, and what are the KPIs? Yes.
Well, first, I'm glad to see that I'm not the only one where enthusiasm gets ahead of myself. But with that, we are at the beginning, at the dawn of a new era, which is so exciting. At the same time, I'm in awe of the vast range of potential new applications. So I think it's exceedingly exciting, especially if you're a PhD student. At the same time, I think it's very anxiety generating if you are involved in big money decisions, investments, whether it's product development or network evolution or even capital investment or venture capital. Because you mentioned recently was drones, where I mentioned the interest of dual use of existing infrastructure that points to urban, suburban, out in the street, although we have this schizophrenia, we know 80% of activity actually happens indoor. And that brings me to the next point, indoor. That's a vast potential of new applications. Maybe not the first one we think when we talk about dual use infrastructure, but how many of you, probably all of us, still remember the action movies where the good guys are outside, the bad guy may be inside the building, and you see the wireframe of the building. At the time, we didn't even call them digital twins. It was just, a representation. And you see the red dot going beep, beep, beep inside the building. Well, we still don't have that 20, 30 years later. Why is that? So I also indicate a little caution. We can let our imagination loose, and this is the time to do so, and creativity is going to come with incredible new potential. But where is the money? Where is the business case? As I said, indoor localization. Recently, anecdote, somebody coming into a huge, large, complex medical university, medical center facility, gets to the reception. I need to go to imaging lab. Nobody really knows. And why is it that I cannot just tap it into my phone and together with AI, ML, guide me there? Why don't we have that? Well, is it that we cannot do it technically? Terrific, fertile area for PhD candidates? Or is it because there is no money there? Or is it because the infrastructure is too expensive in reference to willingness to pay? Very exciting times. Tremendous amount of a variety of new deployment scenarios and opportunities, but also challenging for those who have to place bets.
Oh, thanks very much. No, I don't disagree with anything that has been said so far, but I think the second question should have been first question. And then after that, we say what sort of waveforms we need and whatever, etc. Anyway, it is what it is. There is a study, there's a group in ETSI, it's called ISAC. Industry Specification Group has been working for the last 2 years on many different applications and services that requires ISAC, integrated communication and sensing. I look at those and look at the KPIs. KPIs, for example, for medical applications goes to higher resolution of detecting the heartbeat. That sort of resolution comes to localization, for example, robotic. Some people say for industry setting, probably it should be sub-centimeter accuracy, but that's more indoor. So it's a various different KPIs is required, depends on the use cases that makes business case, that people can make money out of it or whatever. But the whole, if you go back to the first question, the whole idea of integration between communication and sensing, why it called integrated is, can sensing help the communication? I think that was one of the major reasons behind it. We can have a better picture of radio environment, traffic environment, and the network more intelligently can manage itself better rather than just doing it blindly as we've been doing most of the signal processing. We just detect, estimate, and make some decision. So I think it is more powerful when we look at sensing together with AI. I believe that sensing helps AI to make a better decision rather than the other way around. And sensing would help the communication decision as well. And the most important part, when we talk to, because we work with lots of operators, we work with Huawei and etc., but all the UK operators are involved, and they want to look at use cases that they can effectively either reduce the cost or there is a new source of revenue for them for the new applications. But the most compelling one that I can say that one is compelling, that is everybody agrees, how can I manage my RAN better, more efficiently? I think that's what something that probably Tong was referred to, the networked aspect. And it's having a sensing with the AI, it helps the communication and resource management, resource allocation, and etc. I think from that point of view, this is the immediate thing that people say that I can identify there is a value in that, I can do it. We have been doing sensing separately to communication. Sensing is not anything new. I mean, you mentioned radars and etc., but it's when we say integration, so how they can help each other. And in terms of the waveform, if you go waveform specifically as it is, nothing is better than OFDM so far. We haven't seen chirping, etc., but is it big enough performance it can give compared to OFDM? And I believe the researchers we discussed, because we are academics or researchers, we need to know how much is inherent sensing information in communication signal first, before we have explicit waveform for sensing. I think that's the first thing. And when you look at that, the first thing is sensing, if it's based on the reflection and detection, refraction of the signal. It reminds me of the full duplex radio problems. How can we cancel interference from each other? And the initial discussion was it will require at least 100 dB suppression between sensing reflected one and the communication signal before we have a separate signal for sensing or waveform for sensing and something else for the communication side. If we cannot achieve 100 dB suppression with self-interference, then we need to go to explicit signaling for sensing and then separate one for the communication one. So that's my answering both questions in one go.
Yes, thanks.
Thank you. So I guess we're looking into the second question, which is with respect to the novel services. And I think there is no question that because ISIC and AI are going to be combining high precision sensing, ultra reliable connectivity, and real time detection making, I think this opened the door quite open for a lot of novel services. I'm taking note of some that I can think of. So first of all, healthcare and assisted living, I think that would be a very important application where we're going to have contact, patients without any contact can be monitored using millimeter wave sensing. For example, for heartbeat detection, fall recognition, I think that's important, especially for elderly, and physiotherapy movement. I think there is no question that the stuff that Sherman work on, autonomous systems and transportation V2X, for example, network, using distributed ISIC is going to be an important application. I think another one is immersive experiences, where we're going to have a context-aware AR, XR systems, which somehow they can fuse maybe device LiDAR with network-based sensing to enable physics accurate, what I refer to virtual object interaction. Another key service that I can think of is something that is becoming relatively hot in part of China and even in Hong Kong, is something we refer to as the low altitude economy, which refers to basically economic activities conducted in airspace below, say, 1,000 meters. Sometimes they even talking about going to 3,000 meters, but probably around 1,000 meters, which is going to be basically enabled by, first is what I refer to the drones. Obviously, I think you've mentioned that. Also this electric vertical takeoff and landing aircraft. And I think there are, as I mentioned, a lot of activities on this in China and Hong Kong, and even at our own university at HKOST now, we're doing a lot of trials on low altitude economy. And I think in this context, the integration of ISIC and AI will be critical for realizing this low altitude economy, because they will be able to address things like the spectrum efficiency, the safety, and operational scalability. For example, ISIC will allow simultaneous environment sensing to, for example, to detect obstacle, as well as at the same time doing data transmission, sharing, for example, millimeter wave or terahertz spectrum. And AI is also going to be important. For example, reinforcement learning can be used to optimize the drone's trajectory, and by doing so, you're going to reduce the mid-air collision. So I think the potential is huge, and as I said, this is one of the key features of 6G, is this integration of sensing and communication.
Having been around a long time, although it's nice to see some others here who have been around maybe as long, I'd like to give you three examples, which kind of are going to be controversial here, but what kind of belies this was I chaired a panel myself at the Mobile World Congress in India last year, and I had all the standards peoples, the head of standards at Nokia and Huawei and Ericsson and so forth were on the panel, and so I thought I would get them going into an argument by making the following statement, that we're overthinking this, and if you build it, they will come, which is a tagline for a famous movie a long time ago, but I meant it in the context of the network. And surprisingly, they all agreed with that, and I was expecting to get a lot of business stuff about we don't have a business case and we need to do that first. But that has been the history of communications. If you go back to broadband, the service providers globally all thought it was going to be TV service. And it turned out the HTML was developed and web surface and internet became the driving application, which was not expected, but drove the revenues and profits. So it came from the computing industry. If you go ahead another 10, 12 years, you got the iPhone showing up, coming from the computing industry in a creative source, not from the service providers or the telecom infrastructure. And more recently with 5G, what is the application that's drove it? It's the one they didn't consider in the standards. Fixed wireless access is the only one that's really making money right now, at least on the consumer side. I know there's some enterprise. So maybe it's overthinking it too much. All this creativity around integrated sensing, that's all good. You know, getting more accurate, being faster, broadband, so forth. But do we really have to know the business case when the history of communications the last 40 years has been, we built it and the applications came from the computing industry, not the other way around. So that's maybe controversial with respect to some who are worried about the business cases, but should we really overthink that too much in this context?
Thanks, John.
Yes. Actually, I wanted to take a step back and, for context, tell you that one of the names that we considered for the workshop in the beginning was joint sensing and communication, which is not exactly the integrated one. And the idea there, and then perhaps this goes to some of the KPIs, the idea there is that you're reusing the infrastructure, or you have dual purpose infrastructure that makes sense, dollars and cents. For the providers and the economy. But the reason why we end up with an integrated one is because we believe that by putting together and by creating the synergy, new and emerging applications will come. And this may include the indoor type of applications or other applications that we cannot think right now. And I certainly agree with John. The history, or at least what happened in the past, is that we thought that something else will happen, and something new came out of the blue, out of the left field. So perhaps it will be the same this time around. But the important thing is to make sure that we understand that we can go step by step, right? So reusing the infrastructure for dual purposes is one thing. Then coming up with an integration that perhaps will open the door for more, for more things, new applications.
I have a few examples for novel services and applications similar to what Khaled just mentioned. One is immersive XR and metaverse, means accurate positioning and gesture recognition enabled by joint sensing and ultra low latency, smart healthcare, which means passive and contactless monitoring, respiration, heart rate, and human activity while RF signal reflections. And of course, one of the application that I have been working on, an autonomous system, which enabled object detection and trajectory prediction in autonomous vehicles and drones using run level sensings. So the KPIs KPI examples are in throughput, latency for communications, sensing range, sensing accuracy for sensing, inference latency, accuracy, model size for AI performance, energy consumption per inference, energy consumption per bit, and also the service availability for reliability. Thank you.
Yes, so for the service and application, what at this point we can see is the AI revolution that we cannot ignore. So in that sense, what fundamental to them are the two things. One is data. Second is if you need to do some real physical type of, especially the workforce of change. So you in the AI community called the world model, or that model, meaning that you have a gigantic model to know everywhere, the corner of the earth. So in that case, the sensing data will be probably more simplified and more easy real time. So in the case, I want to put two things. One, just follow the previous. We discussed about the complexity of the thing. So one is for indoor. In that case, let's say if a 6G device is not broadband communication because it's all Wi-Fi dominant, but what is important is that they will have many point cloud. So that will enable all the service provider or even the AI provider to have a reconstruction of the indoor information. It's not the location that is important, but it is the structural environment of indoor that could potentially be a big value. Then all the service you can build on. And the other one for the outdoor case, looks like SpaceX will provide the service of a real-time broadcasting of the Earth sensing with some less than 1 meter accuracy. So that it will be can be integrated with the mobile network to have a complete. You say digital twin, or my point is, the location of that single device may not matter that much. Then you have the full knowledge of the so-called ambient. That is where potentially AI service could be really useful.
Struggling with the question as to whether we're talking about integration of sensing and communications at the physical layer. But when you switch the discussion to applications, I naturally think about protocol stack and how to expand from, let's say, a set of services that you can introduce at the physical layer and provide services to support other applications as part of the protocol stack. It's not clear to me. The other part that's not clear to me is we can look at the RAN architecture, and it's got the data collection, and it's got the ML, and it's got orchestration. But how does that relate to the type of data that you can collect in communications and sensing? Again, is it the same structure that's handling both, or is it something parallel and separate? It's not clear to me.
Are you moving to question number 3?
Yeah, we can come back to the first two items later if we have time. So now we are moving to the item number 3. How can AI/ML algorithm jointly optimize communication, sensing, and computation in the 6G RAM, adapting to dynamic conditions and applications? Who would like to? Yeah.
Okay. Sorry, I'll go first this time. Because I share with you some of the research findings that we had. First, looking at the AI and communication. One example that we thought that AI substantially improved the performance of the wireless system is it helped us to have a much reduced CSI channel state information transmission for massive MIMO than we traditionally do. The feedback channel was a lot less. So this is one aspect. The second, another aspect was that we've done is for the communication is using AI in form of the semantic communication. I think Khaled mentioned this one earlier on. We can reduce the volume of the image or video substantially to the extent that we use this one as an example, say that even for the GSM system, the 2G, which we couldn't transmit image, now you can transmit video. And it's high quality video with the semantic communication. So that's another aspect. Another aspect is, I think it is sensing helps the AI rather than AI helps the sensing. I think that's probably it's the other way ran more effective than AI helping the sensing. And I think this, when we have AI and you have environment sensing, I think this is something that Tong mentioned, is you can reduce the point cloud information substantially, and that helps with the computation as well. And you have a better picture and view of the radio environment, more intelligent, that it can cope with the dynamics of the channel, whether it's indoor, outdoor, whether it's robots can learn their own environment by doing this combination of all of this. So I stop at this point, and I've got a lot to talk about, but we'll give a chance for others to contribute.
Thank you. So certainly, I think when we're talking about how we can use AI and machine learning to optimize communication, sensing, and computation, there is no question this is going to be important in the context of 6G through what I refer to as intelligent coordination across different protocol stacks. And I just want to basically focus on a specific method, perhaps, which I refer to as federated learning, I think, which has really the potential to play a very important role by coordinating distributed inference tasks across the devices while preserving the privacy. So the way federated learning works is that instead of basically using the data of the devices, we basically keep it there, and then we only send aggregated, say, gradient or something, either to the cloud or to the edge. And by doing so, we can do learning, machine learning, but we can preserve the privacy. And I believe that federated learning, a lot of it has been used at the cloud, but I believe that the use of federated learning at the network edge could actually have can play a much important role, and this leads to what I refer to as federated edge intelligence. And recently we had a JSEC paper that was published a few months ago, basically where we use what I refer to as split learning to basically partition DNN models across the devices and the edge server, so we don't go to the cloud, in order to optimize basically the communication, sensing, and communication. So for example, in the context of communication, we only transmit intermediate features. In terms of computation, we can offload the complex layers to nearby at the edge servers. And in terms of sensing, we can simply share calibration data between co-located sensors. So I think I just want to say that federated learning is going to be very important in this context, and I truly believe that the use of federated learning at the edge of the network can even be more significant.
Thanks.
So maybe let me focus on perhaps detail, but growing an importance topic. When it comes to AI/ML, I'm kind of the hands-on engineer that wants to understand how you make things work. And it's been proven that with the AI/ML, various proof of concepts have been, or simulations have been carried out and published, that you can indeed do great things. What worries me is that it takes considerable effort, especially if you're doing multi-party computation or federated learning. How does the model adapt when you have a sudden change in the environment? So the user moves from indoor to outdoor or around the corner. Do you retrain? Do you pull out a different model out of memory? Or how exactly does this all happen? I think we have interesting results, as I just said, but they tend to be within one single type of environment. And so the next challenge, I think, exacting question is, how do you make it work in the real world with the dynamics? The word dynamic, I think, is very apropos.
Yeah. Oh, that's actually. Oh, I'm sorry. That's actually a very good point. And the thing is that it has been, the whole system can be introduced in a different setting, in a different paradigm. So how you apply something that has been constructed for a different set of circumstances, to this dynamic and changing environment is a big question mark. It can be as simple as, changing the cardinality of the nodes that participate. So you start with 5, then you go to 3, and then you go again to 10, or you lose connectivity, right, with some of the other players. With your permission, I also like to jump ahead a bit on the question number 4, because question number 4 has to be considered, in tandem with 3, because the real important thing is the data. Do you have the data, and do you have the high quality data that you need to train all these models? The majority of the tools and the methodologies we have right now, they're coming from a different paradigm, right? Mainly computer vision, right? And consumer-style computer vision, where basically the data are plentiful, and there is a good, agreement on what constitutes a good label. We're talking about, machine learning, label data, etc., etc. So you can see a dog, you say it's a dog. You can see a raccoon is a raccoon. The question is how you will, what kind of training data in the electromagnetic spectrum, for example, you will have, and how you will, label them, and how you can make sure that all of us agree that this is the right label for this kind of stuff that, the time series that we see, either in the time domain or in the frequency domain. So these are, things that they affect the quality, so to speak, of, the algorithms that can be applied in for and sensing.
So a quick follow-up, and I really love your point there. And maybe bringing a little bit back the controversy in case some of you guys are having mid-morning tiredness. Quality of the data. So as we venture in joint communication and sensing, and we think that perhaps every phone, every time can be feeding data into the system. Well, there is a little dirty secret. A lot of the very amazing utilization of AI/ML in the early days relied a lot on data, labeled data. And the dirty little secret is we had this digital Turk labeled data, where humans were actually paid, pennies to by hand, dog, cat, dog, cat, dog, cat, and then the machine does it. Oh, wow, it's amazing. Well, that was not very artificial. There was a lot of human input in labeling that data. How do we do it with the cell phones? So if you are going to be accessing your data from your physical layer radio, who is going to be the digital Turk that is going to add a KPI? Is it all the noise? Is it only background? Is it target? Is it the object you are interested on? What is it that you're interested on? How does the information goes down to the radio to say, I want to detect a car, or back up to the higher layers of the protocol saying, I see a car, or it's just noise? I think these are fascinating questions in terms of not just collecting massive amount of multi-party data, but labeling it.
So for the third questions, there are several potential approaches in my mind. One is the multi-objective reinforcement learning to balance trade-offs between communication throughput, sensing accuracy, and computation latency. Another approach is online learning and adaptation, means continuously adapt to dynamic channels and the mobility without retraining from scratch. And also the traditional cross-layer design, which we are familiar with, that is integrate AI across physical, MAC, and network layer for end-to-end optimization. Means, for example, beamforming plus handover plus task offloading, etc. And the last one in my mind is hierarchical and distributed learning. Means combining global cloud-based with lightweight localized AI models at the edge for context-aware and low latency decision making. Thank you.
Thanks, Sherman. So probably we move to the next item. Number 4 is how can we collect and enable sufficient high-quality training data set in real-world wireless systems? And how can we share the training data set in academia and the industry? Thanks.
I think the answer I wanted to give you, the question 3, it applies to question 4 as well. It is not just the quantity of the data or the quality of the data. It is more about, for AI, is a diversity of the data, which is important. That's what I said, sensing helps the AI, because that brings the diversity and various information for the data to learn much quicker. And I think some of the data can be real time, can be true data, and to smaller volume, you have to know how to synthesize the data. You know, it is not only just relying on actual data. It's a combination of real data and synthesized data. We have to be careful how you generate the synthesized data. I think and it helps that. So I would say that, going back to question 3, the inference models have progressed substantially. I think we see the pace of improvement in AI training and inference and etc. is mind-boggling, to be honest, how fast it is moving. And even computation, I think every year by a factor of 1.4 is the computation and energy consumption is reduced. So, for example, if you say 6G, 2030 plus, and etc., then I'm just wondering how much we can do improvement on that. So I would say that, and going back again to question 3, I mentioned as well that we work on the channel state information. In 3GPP, there is a huge amount of data, measured data, simulated, synthesized data, and the channel models are available. And we use those, and then we compared it with some of the measured data, and it worked. It is really good. The inference models, that etc., that it gave us confidence that probably we can have a good universal channel, universal technique to do CSI estimation, or with a very reduced amount of the data that we can transmit for the feedback on that one. So I would say, to summarize, the quality is important, but diversity of the quality of the data is very important. That's why the sensing helps AI, right? And that's AI purely just work on that one. So.
Thanks, Rahim.
Yeah. Okay, I think that is a question is also related to Rahim's point. That is the one topic about the synthesized data, but not only the real world collection. So actually there is some real challenges in collecting the real world data. For example, the real world is changing from time to time, and you cannot exhaust all the scenario to get the real world data. And secondly, then due to the complexity of the hardware problems, so you got the data, you have to make sure this is high quality. So in sometimes we cannot totally rely on the real world data we collected. And also I would like to talk about I recall this one computation I was involved as the organizer called the AI for wireless communication computation. In that computation, we also collect the data shared for the competitors. And in the beginning, so we just got the real world data, and we thought it is sufficient. But when we checked different SNR scenario, different mobile speed, and then it does not work at all, because this real world data is quite limited. And we cannot just say that this data we collect can be applied to other scenarios because it's a specific application. Then we think about how we can just augment the data by learning the real world data, and then by including some, for example, OpenStreetMap software to simulate this real world environment, and then add some ray tracing the data. Then we put it all together, synthesized data, and then that can make the data to be diversified. And that is one effective solution. Yeah.
Very quick comment. To again follow up Reinaldo's question, that is a key part, that the model, likely we have to give up a universal model works everywhere. So that will be bring to the locality of this AI thing. And it will be become a unique feature for the carriers. So that's, go back to John's question. So if it's still the superscaler can still do the overlay OTT service, or they have to somehow get into this physical reality to deliver a high quality AI service? This is an unknown question. If this is true, then the whole network is in the business with AI. Otherwise, it will be still, we don't know where is the driver of the application that eventually will take the the communication to the next stage.
Yeah, in my non-academic context, I had a very significant opportunity to look at data for both wireless and wireline systems. And as we progress towards federation or use of AI, as you're describing, I think there is an opportunity to kind of opening up. We've talked about it with APIs and Open RAN versus AI RAN and virtualization. I believe that there is an enormous opportunity for service providers because they do have that data, they own it, and so they're reluctant to provide it or to make it available. There are some efforts like that ongoing. I had the opportunity to talk to Mr. Bartolo, who's the CEO of the Aduna, which is spinning out of Ericsson, but it has many, many service providers, and it's an API. And I asked him, would it be possible to get it down to the physical layer? And they weren't initially anticipating that, but it is possible to do that. If you talk to, and I've talked to senior people at Facebook or Meta now, Google, other places, they would be willing to pay for that data, to use it for AI, to correlate it against, as opposed to a concept that's kind of big in Europe right now with service providers, which is, we built these networks and the application providers should be taxed to pay for that. That's probably never going to happen, and it's not really a fair idea. But they do have data that if they were willing to make it available, they would pay for that data. So it's not a tax, it's a value that they're doing. But instead of trying to do all the applications themselves, making that available so that anyone and all the creativity could come to bear, using that data, using AI, protecting it as federated, like you said, not necessarily giving away the consumer's identity. You don't have to do that necessarily with this type of thing. You can anonymize it. Maybe that's a better solution. And it opens opportunities to make a lot more money by letting so many have access to the network and take advantage of it, rather than trying to keep that kind of under control. It does meet a lot of resistance from service providers. They don't like giving up that data. It's something they feel is theirs and could compromise them in different ways if that happened. But that would be a great trend, because I think everybody would benefit and make more money as an industry without necessarily having to know the killer app, but open it up so everyone could have access and take advantage and charge for it as you do that.
Yes, thank you. So let me narrow it down to a personal experience and very specific point, perhaps a detail, but I think it brings up a little reality again. So going back a few years, as AI/ML became very hot, and being a propagation modeling measurement kind of guy, I thought this is ideal marriage made in heaven, because in propagation modeling, we have an environment that is so complex that if you try to apply electromagnetic theory, we have a lot of formula, we have a lot of simplifications, but then at some point you give up and you get, have a cloud of points and you do a regression and you get a, slope and intercept, and it's served us very, very well in the cellular industry over many decades. And I thought this is ideal scenario for AI/ML. So let's have some smart guys that do not know that this cannot be done, and let's just ask them to do it. So they start doing it, and then after a few weeks of very intense work, they have a solution. Then comes Reinaldo, old-timer, and says, okay, now let me test your model and ask it to predict propagation in free space. Boom, total disaster. Why? It was not part of the training data set. And this opens up a very interesting question. In electromagnetics, perhaps in other fields, but certainly close to my heart, we do have good understanding of theory in a range of canonical cases, as I call them. Free space, ground bounds in open field, maybe even indoor at the lower frequencies where the finer detail gets blurred by the wavelength. You can do ray tracing and it's fairly accurate. How do we, so then it becomes a very interesting in the kitchen cook kind of guy. You could generate a lot of data by computing the formulas on electromagnetic fundamentals and generate that data set of, canonically computed data. But now how do you prioritize? Do you do that 10%? Is that 20% of your data set? Because we know the outcome of whatever model you apply is going to depend on your input data training set. So do you do 50-50? I think this is area where it's just at the beginning, because there is a lot of mindset on just give me all the data in the world and the block box is going to do it. Or we have the perhaps older fundamental guy saying, no, I'm going to do electromagnetics and I'm going to predict the world, which is impossible in its infinite complexity. Where is a nice middle where I illuminate or inspire the AI/ML with interesting fundamentals-based data points? I think that's an interesting angle.
Thanks.
Yeah, so I think the point is that we don't need to use AI to optimize. We know already optimized. That's what.
Perhaps actually a comment. The data quality actually is one aspect that has been neglected so far in the entire AI type of industry. The notion of data quality is not really data quality is only important. The knowledge that the machine can actually get from the data is important. And that's what we need to actually start looking into and start performing research. What is a model can get from a particular data? That's a knowledge. How do we basically express the knowledge within the data? That's the main point. And there have been some work actually that we are actually taking to IETF and IEEE and IRTF, that they are looking at what we call data descriptors and data topologies. So this is basically based on what model can actually get from a particular data, what knowledge it can extract from the data. And if we can actually build that, this notion of data descriptors will actually get itself into what we call the data topologies, then we can actually use, regardless of whether we are doing centralized training, distributed training, federated learning, or sequential training. So that's one point that I want to actually take across. And so there need to be some research in this area in terms of how do we know what knowledge basically is suited best for what model. Thanks.